Hello, and welcome to this product-focused discussion on Sicoya silicon photonics. My name is Mike Davis, and during the session, we'll go over an introduction to Sicoya and the technology, current product offerings, and then how this technology lends itself to innovative solutions for co-packaged optical switches. So integrating optics and electronics is really what Sicoya is all about. So on the left, you can see some optical and electrical building blocks, which we're able to integrate into our designs into the same monolithic chip. So these could include optical functions like modulators and photodiodes and waveguides and splitters, and also electronic building blocks like transimpedance amplifiers, limiting amps, clock and data recovery circuits, digital diagnostics, monitoring blocks, things like this. So these can all get pulled into one monolithic chip, which becomes the main component of an optical module. So a little history about the team. The group was founded in about 2008 at the Technical University of Berlin to refine the process of integrating electronic and photonic elements into monolithic die. So with that university funding, that enabled the team to co-develop the process with a commercial foundry. And as a result, the team developed many building blocks on an 8-inch by CMOS process and developed advanced PDK and IP. So we now enjoy the exclusive use of that IP. Sicoya as a commercial entity was founded in 2015. And the target market of Sicoya is to productize and target products for hyperscale data centers. Our first product was a 4x25G PSM4 QSFP28 module utilizing Sicoya's EPIC technology, which is shown over here to the right. And that monolithic die in the center of the paddle card is essentially a transceiver in a chip. Has all of the electronic functions, electronic and optical functions required for high-speed data transmission of 4x25G transmit and receive. We'll show a little bit more detailed look at that in subsequent slides. But that was our first product. Sicoya is headquartered in Berlin, and currently we employ about 80 people. Of those 80, there's a mix of production and R&D and management and whatnot. So as I mentioned before, the EPIC have a common front end integration of electronics and photonics. So here's a view of how we achieve that. We essentially start with a SOI wafer where all of the photonic elements are placed. So modulators and waveguides and things. And for the area that there are no optics, that area is etched away. And in the place of the SOI that was etched away, we selectively regrow silicon, and that's where we put the electronic components. And then the top 5 to 8 layers of metal backend are shared between the SOI and the selectively regrown silicon substrate. So if we take a closer look at the 100G PSM4 design, you can see the different functional blocks, both electrical and optical. So here you can see the optical ports and grading couplers for the 4 transmitter and 4 receive ports, as well as some test ports for wafer level testing and things like this. In this section, you have the 25G NRZ TIAs and photodiodes. This is a really key feature of our co-integrated process, actually, is how tightly coupled the TIA and photodiode are. So physically, they're very close to each other, so very good RF performance due to low crosstalk and low noise. That's actually a really critical piece in receiver sensitivity metrics. In terms of electronics and digital blocks, you can see the 4 transmitter and 4 receiver clock and data recovery circuits, as well as the 4 modulator drivers and modulators. Furthermore, in the top right and bottom right, you have the digital control blocks and the 2-wire interface. So that's the EPIC. In the bottom left, the one piece that didn't want to forget is the continuous wave laser. So this chip itself doesn't produce photons, but uses a single mode CW laser for its optical input. So here's another look at the CW optical input and how that's used in the chip. So the package laser that was pointed out a second ago comes in to the optical chip through a grating coupler into the waveguide into a splitter where it's independently modulated by 4 modulators. And then each channel is sent on its way out of a grating coupler and into the optical coupler. That coupler is shown up here in the top right here. Wasn't shown in the previous pictures. On the receive path, similar things happen. You have optical receiver light coming in, hitting a grating coupler, hitting a waveguide, and then hits a photodiode, which is, like I mentioned, just very, very short reach to the electrical portion of the chip. So a matter of a few microns away. So that is the path that the receive light takes. So now that we understand how the technology operates, we can take a look at what we offer as products. We offer 4 things currently, and starting at the left, we offer a SiP 28 long reach 10 kilometer transceiver with an industrial temperature range. This is for a 5G outdoor wireless applications. So the EPIC itself is very stable over temperature, as we will see. So it lends itself well to uncontrolled temperature extremes. Moving on, as we've discussed, the 4x25G PSM4 is our 100G offering. In our 400G class products, we have 400G DR4 Plus, which is a 4x100G PAM4 2 kilometer parallel single mode optical transceiver. And then finally, the 400G FR4, which is a 4 wavelength by 100G CWDM type interface. So some highlights from the DR4 Plus product. So this is a DR4 Plus transceiver with multiple options. We're able to support an MPO, traditional 8-fiber MPO connector, or a new type of connector called an SN connector, which is common for breakout type of configurations, and then also integrated patch cords or pigtail options, both in QSIP PDD and OSIP form factors. Product is based on our 400G EPIC, shown here. This one is featuring the 2 lasers, both at 1310, and then we're seeing 10 watts with our worst case with our current generation, with a path forward to about 8 watts per device in total. Operating temperature standard 0 to 70 C, and then all the nice digital features of CMOS 4.0. So now moving on to the 400G FR4 part. It's highly related to the DR4 part, and it actually shares a common component, the 400G EPIC. But in this case, we use the 4 lasers for the 4 wavelengths for the CWDM grid. the EPIC itself is running in parallel, so we rely on external mux and demux to get the colors, on and off the single fiber. So as I just mentioned, the 400G DR4 and FR4 engine have a common component, which is the 400G EPIC. So the 400G EPIC is essentially a totally integrated 4x100G PSM4 or FR4 engine. The difference being how the external light sources are configured and populated. So this chip is essentially in a completely integrated linear modulator and driver on the transmitter side, and then a linear pin and TIA with controls on the receive side. Practically, it is a prototype co-packaged optical silicon photonic chip. This has a USR type electrical interface, which is not exactly defined yet, but it is a low loss electrical interface to interface from a DSP or a switch to the silicon photonic engine. So this as a building block fundamentally is similar to future things that we will show for CPO applications. So next we can look at the 100G transmitter performance. So here we're showing the modulator and the driver performance. The modulator has a bandwidth of about 35 gigahertz. But so next we can look at that transmitter performance over temperature. So what we have here is a sweep from 15 degrees Celsius to 85 C. And you can see the very stable performance over temperature. This particular test was done on a wafer level. So we used a wafer prober with a remote laser source to do this test. So the laser, was 10 feet away and was temperature stable. And the EPIC was heated and cooled at the wafer level. I mentioned the remote laser source because it will become more apparent later why that's important. So very stable temperature performance, transmitter performance over temperature. And this is just another view of the same data, just showing qualitatively the 15 degrees C and the 85 C eye diagrams. They're virtually identical. So moving to the receiver performance, we have 2 bit error rate versus OMA curves shown here. The left one is showing basically the 100G PAM4 stress receiver sensitivity relative to the 400G DR4 limits. And you can see the stress receiver sensitivity is around minus 7 dBm for the OMA outer. So a couple dB margin relative to the 400G DR4 spec. Most of that performance is probably due to the photodiode bandwidth. So we're showing the photodiode bandwidth of greater than 65 gigahertz, which translates to or contributes to nice sensitivity numbers. On the right side, you can see the almost the same data, but a little bit different test. So the optical power has been increased, and we're testing overload performance here. And what we can see is that there's no aeroflow and quite a bit of margin relative to the maximum output power of the 400G LR4 spec, and that's the highest optical power, standard in the 400G world. So, and that nice overload performance is due to the integrated variable optical attenuator that kicks in our EPIC at high power. So I think shows a nice feature and benefit of integrating the optics and electronics. So far is where we are today. And I guess the question might be where we might be headed next. So to help answer that, we can look into the past a little bit to maybe identify some trends, and then see where that leads for future possibilities. So what we'll look at is a history of pluggable interfaces in data center switches. So going back to say 10G, what you have is essentially a switch on a host board with an unretimed link to a pluggable module. So the channels were such that you could perform error-free links without a retimer in the middle of the channel. So that maybe for 10G was acceptable. Moving to 25 and 50G wasn't really possible to accomplish that any longer. So what was decided was to put a retimer, shown with the star here, into the optical modules to retime the data just before and just after the optical interface. And that was sufficient for some systems for error-free performance. Other more challenging systems, this third one, you might see a additional CDR to be placed on the board. Again, doing what's needed to make error-free transmission. So those are all pretty typical architectures for pluggable interfaces. Another kind of somewhat common in certain circumstances interface is to actually pull the an optical module into the board. We're calling that an embedded optical module. And in this case, the data is retimed in the optical module, and typically this is only done in the cases where pluggable modules don't provide a dense enough solution. So very high port count, high throughput applications might use an embedded optical module. So these are all somewhat common and do exist in the market today. Moving forward to future concepts for pluggable I/O, I think we will see with the introduction of a 52 terabit Ethernet switch, the introduction of this concept of co-packaged optical switches. So two major changes in this kind of architecture. One is the movement of the optical module from the motherboard, from the host board to the ASIC substrate. This piece here, we're calling it an optical tile. In this version would be likely a pluggable interface that may be defined by an MSA. So that's one major change, the movement of the optical module. And then what you might see as well is keeping the laser source in a place where it can be maintained and replaced if it wears out. So so we're showing a remote laser source at the faceplate such that it can be repaired if needed. We realize that photons could be created in the optical module, optical tile as well, but we're just showing it here where the laser is in a relatively cool spot and that can be maintained. So we're calling that a tiled CPO based on the optical tile. Finally, what we might see is what's being called co-packaged optics with direct drive. So the host switch here would be directly interfacing silicon photonic die. So that may become the, say, ultimate version of the CPO. So the question might be, why would someone want to build optics into the system? Practically, you wouldn't want to do that unless you had to. Why is this happening? One example of an application where you might see these co-packaged optical switches are these high capacity mid-tier data center switches. These are basically these mid-tier switches here. Their function is really for providing east-west routing and traffic for large hyperscale data centers. So all of these connections go from one switch to another, and they're physically placed in such a way that practically they're all optical I/O, right? So practically 100% of the ports are populated with single mode optics. And so if you're in a position that you know that 100% of the ports are going to be optical, you might do things to optimize power and cost. So I believe that's really the purpose of why you might want to integrate photonics into the system, benefits could be really high in both power and cost reduction. Power reduction due to elimination of or reduction of requirements in electrical channels, and then cost reductions due to elimination of components, and then increasing the volume on a given design. So here's a look at where you might find Sicoya EPIC in co-packaged optical switches. So we're showing the two versions, the tiled CPO and the direct drive CPO. In the case of the tiled CPO, you have an interposer with DSP and the silicon photonic die on a pluggable interface. The electrical interface between the DSP and the EPIC is a yet to be defined USR interface. And then between host ASIC and the EPIC tile, the CPO tile, would be an XSR electrical interface. So this is an attractive solution for those looking for a pluggable solution for compatible multi-source agreements. And also for maintenance in case something fails. So those are the two main benefits. One of the major driving factors of this type of design is the interposer and the connector. The connector pin pitch really defines the length of this XSR reach. So the bigger the pin pitch, the further the traces need to be able to route to those. So by integrating a connector, essentially you are defining it to be an XSR type reach electrical channel. An alternative that we see as a possibility is to integrate the EPIC die directly onto the substrate. So the EPIC could be reflow soldered directly to the chip substrate, and then in that case, yes, it would be permanently fixed there, but you could reduce power and cost by eliminating the DSP and the connector. So these are both potential options that we see. In our case, we are somewhat indifferent because it's practically the same EPIC. Both would be essentially 3.2T EPIC with USR electrical channel. So either way, it's the same chip for us, but our integrating electronics and optics into this EPIC too is critical too, because it becomes a impedance matched electrical channel. So it would be, instead of driving a modulator, if it was a just a bare PIC, might be somewhat problematic. But in this case, it's driving a USR electrical channel, for the main benefit of potentially eliminating the DSP and the connector. So by removing the requirement of a socket, one could reduce the reach of the switch to optics trace. So we estimate that the trace length would be reduced from about 50 millimeters to about 20 millimeters. And we've done some simulation work in terms of what that gets you in terms of signal integrity. So it looks to be about a 4 dB improvement on the longest trace between a direct drive CPO and a tiled CPO. And here's a view of the difference in size between the direct drive CPO and the tiled CPO. So you can see on the left side, the tiled CPO with a given socket pitch would yield a total substrate size of about 90 millimeters by 90 millimeters. And on the right side, with reduced pin pitch of directly soldering the EPIC to the board, could reduce the size down to just 50 millimeters for the substrate. In these two pictures, it's a little bit of an optical illusion, but the center, ASIC squares are the same size. So significantly reduced substrate size if you're able to integrate the EPIC directly onto the host ASIC substrate. Furthermore, I wanted to mention the power reduction that could be achieved as well. With the tiled CPO, with including the DSPs, could be up to 900 watts for the substrate, compared to about 600 watts if you eliminate the DSP. And another critical piece of the co-packaged optical switch ecosystem will be the remote laser source. So we imagine a pluggable, field replaceable remote laser source that would either be in CWDM configuration with 4 different wavelengths provided by the remote laser source, or DR mode or parallel single mode supplying a single 1310 nanometer wavelength. There are another number of concepts being discussed in the market. So here you can see AOI and Sumitomo Electric have both developed concepts, which we're showing with their permission, and thanks guys. And essentially the purpose of this is to provide all the optical power, the unmodulated optical power that can be passed to the EPIC for modulation, and then passed to the output. The purpose of putting these in pluggable modules is for field replaceability and for maintenance purposes. So this is a critical piece. There is not yet a defined MSA, however, so this may be something that the industry should look towards. So bringing this all together, we imagine the possibility of a CPO switch that could be configured at the faceplate. So there are two main types of applications of the CWDM or the parallel single mode, both of which could be configured at the faceplate. So what you could imagine is having two types of remote laser source, one with 4 wavelengths, sourcing the CWDM wavelengths, and the other with a 1310 configuration with many lanes of 1310. Both passing to an EPIC to be modulated, at which point it would be passed back to a fiber IO kind of pluggable module, which would then determine the final type of media that the output would be. So you can imagine these type of pluggable configurator modules would maybe contain optical mux and demux, so that the individual wavelengths would then be muxed at the faceplate level. That could be swapped out with a type of module that keeps things parallel, right? So no longer muxes them, but instead, keeps them in parallel single mode configuration. So such a switch would be very powerful in terms of keeping overall costs down. So inside of the box could essentially be the same, depending on whether you configured it for DWDM or WDM mode or PSM mode. Okay, so it looks like there's a number of questions. So hopefully you guys can hear me. I'll just start with the Q&A questions in the box. There was a question about preferred cooling method for the EPIC, which I just answered. I guess the question is, suggested thermal solution. We imagine a common heatsink shared between the host ASIC and the CPO tiles. So we believe a single common air-cooled heatsink is sufficient for at least a direct drive type configuration. Next question, how do you burn in the laser source for your 400G DR4 Plus module? We do this at the packaged laser level. So the little box that sits on top of the EPIC, which I pointed out a couple times, that piece is actually burned in prior to assembly to the EPIC. Next question, what size is the remote laser source? We've seen different configurations. Practically, they fit in standard pluggable form factors. So QSFP-DD or OSFP. So they're something around 2 to 3 centimeters by maybe 5 to 7 centimeters in a pluggable standard form factor. The actual dimensions are defined by an MSA, so you can look this up. What is the best uniformity you can reach in the waveguides? I don't have that data on hand, but channel to channel, it's very uniform. When can the advantages for CPO translate to benefit for the industry, I guess? We imagine really it will be the introduction of a 52 terabit switch would be the first design that could possibly take advantage of CPO, and earliest this would be about 2023. So 2023, you might see 100G SerDes on a 52 terabit switch. Some designs will, of course, take advantage of the standard, pluggable type architecture, and then some taking advantage of CPO type designs. And then I think, let's see, that's all I see from questions. So thanks, everybody.